Okay, Assalamualaikum and a very good day to everyone. Okay, my name is Nur Alawiyah Abdul Aziz from School of Mathematical Sciences, USM. So today's seminar is on the theory of domination in graph and hypergraph by Professor Nader Jafari. And there will be several talks on this topic, and today is the first talk. Maybe the next talk will be in 2 weeks. So before we proceed with the presentation, let me tell a bit about our speaker today. So Prof. Nader is a professor of mathematics, and he is currently the head of the Department of Computer Science at Shahed University, Tehran, Iran. He received his PhD degree in 2007 from University of Mazandaran, Iran, in the area of graph theory and combinatorics. He started his career at Department of Mathematics, Shahrud University of Technology, SUT Iran, as an assistant professor. Prof. Nader then joined the Algorithms and Computations Group at Institute for Research in Fundamental Sciences, IPM. In 2009, my name is Nur Alawiyah Abdul Aziz from School of Mathematics and Computations Group at Institute for Research in Fundamental Sciences, IPM. Master students in 2009 and students from different universities. Prof. Nader has been appointed an academic fellow of School of Mathematical Sciences, University of IPM. He has done research on several topics such as extremal graph theory and universal theory, algebraic graph theory, coding theory, and algorithms and complexity. His main research interest is domination theory in graph and hypergraph. To date, he has published more than 170 papers in mathematics journal and 2 single book chapters. He has collaborated with many mathematicians from many countries, including from Nigeria, Canada, China, France, Germany, Poland, Spain, and United States. So I think without further delay, I pass this session to Prof. Nader. Prof, I think you can start your presentation.
Okay. Thank you very much, Dr. Alavi, for introducing me, and thank you to all of you. Thanks to all of you for being here in this talk. I should also thank very much to the School of Mathematics of USM for giving me this opportunity, and thank you to all of you. This talk is the first talk of a series of talks. I should also domination, the theory of domination, this in graphs, hypergraphs, and in this talk we mainly pay attention to the introduction of this theory. A series of talks. In this talk we first discuss about some definition and example. We present some example talk. We mainly study and report the background, historical background of the theorem, the concept of domination and the theory of domination in graphs, and then we report some results, talk about coin graphs, and then we state some applications of domination, the concept of domination, and then as the main and then topic in this talk, one of the most topics is the presenting the most operands in the area of domination. We then report some algorithmic and complexity aspects of domination in graphs, and finally we introduce some models of domination in graphs. We then, as a definition, a subset S over T set aspects of domination in graphs is called the dominating set. If every vertex outside S has a neighbor in S, the minimum combination of such set is called the domination number, and the domination number of a graph G is equal by gamma G. For example, here you see two graphs. The left side graph is called the red vertex, and a domination number of a graph G because by any other vertex is adjust. For example, here you see two red vertex, and left side graph, since the domination side graph is the red vertex, this is a minimum of the graph G. So the domination number of this graph a positive integer, this is a minimum dominating set. So the domination number of this graph is 1. In the next graph, in the right side graph, you see two red vertices that any other vertex is adjacent to at least one of them. And it can be easily checked that you cannot find one vertex to dominate all vertices in this graph. So this is the minimum dominating set in this graph, and the domination number will be 2. Here is another example, the famous Petersen graph. You see the Petersen graph, and in the left side, you see five red vertices that they form a dominating set. So we have a dominating set of cardinality 5. In the middle graph, you see a dominating set of cardinality 4. And the right side graph, you see a dominating set of cardinality 3. It can be easily checked that among all possible dominating sets, for the Petersen graph, the minimum cardinality is 3. So the domination number of the Petersen graph will be 3. As another example, for the classes of paths and cycles, the domination number will be n/3. For example, here you see two paths, a path of order 6 and a path of order 11. In both paths, you see the two red vertices, that the red vertices form a dominating set. And sorry, Professor, Dr. Alavi, you hear me?
Yes, Prof.
Oh, okay, sorry. Here you see two paths with dominating sets that are in red vertices. But if we want to prove that the domination number of the path Pn is equal to n/3, what is the proof? One part of the proof is providing a dominating set of the desired cardinality. So you should present a dominating set of this cardinality, n/3. For this part, we divide the problem into two cases. When n is equivalent to 0 on modulo 3, then this set is a dominating set. It can be easily checked that this is a dominating set because any other vertex is adjacent to some vertex in this set. And for n not equivalent to 0, also similarly, this set is a dominating set, and their cardinality is n/3, so the domination number is bounded above by n/3. So here we prove that the domination number of the path Pn is bounded above by n/3. But how we should prove the equality? For this, we need a different argument. And in this simple example, on path Pn, you can have such argument. If you consider any dominating set S in the path Pn, any vertex of S dominates at most 3 vertices of the graph. So S dominates at most 3S vertices of the graph, and 3S should be greater than or equal to n. This gives S is at least n/3, so the lower bound will be proved. Okay. We next study the historical point of view of the concept of domination. The historical point of view of the concept of domination come back to ancient India for problems in the chessboard. In the chessboard, you know that there are a lot of chess pieces that moves under some conditions. One of the most problems was that was for queen, a chess piece, namely queen. This is a queen in the chessboard. This chess piece can move vertically, horizontally, or diagonally. The problem is here is that how many queens we need to attack all squares of this chessboard. And the next problem is, what is the minimum number of queens to attack all squares of this chessboard? This problem was later named as 5-queen problem because the answer was 5. And you see here 5 queens that attack all squares of this chessboard. This problem was asked by Janisch in 1862, and similar problems has been proposed by Ball with some other conditions. For example, one problem is that how many queens you can put in the chessboard that attack all squares, but they not attacking each others. This current problems was named as independent covering, that later we will refer it as independent domination. Similar problems was proposed by several authors and researchers. To find the minimum number of queens to attack all squares of the chessboard, for n up to 13, you see the answers in this table. For example, as you see this in this below row, for a 8x8 chessboard, the answer was 5. And for example, for 12 by 12, the answer is 6. The approach and the proof for this table was number theory. But for other n, this was difficult. Berge called the idea of the queen problems and domination problems as the coefficients of external stability, and Ore in 1962 used the terms of dominating sets. One of the most players in developing the concept of domination is Vizing, who asked a question on the domination number of Cartesian product of two graphs. Many researchers tried to answer the Vizing conjecture. I will explain more Vizing conjecture later in this talk. The brothers of Yaglom in 1964 asked similar problems, similar to queen problems, for other chess pieces like rooks, knights, kings, and bishops. And finally, in 1975, Cockayne and Hedetneimi survived all results published by that time. Several efforts on Vizing conjecture has been done by several authors, and you see here some of them. The number of papers published and work in the concept of domination in graphs by 1998 was around 1,200 papers. And by now we have more than 4,000 papers devoted in the concept of domination in graphs. And this shows that the concept of domination experienced rapid growth. The main books in the area of domination are the following books. Book 1 and Book 2, published in 1998 by Professor Haynes, Hedetneimi, and Slater, under the name Fundamentals of Domination and Domination in Graphs. We call these books as Book 1, Book number 1, and Book number 2. After passing away, Professor Slater some years ago Haynes and Hedetneimi decided to continue and updated the current results, the old results in the domination as new books, and they decided to write new books. Here you see a book, we address it as book number 3. This book will be published the coming year, next year. It is under name Domination in Graphs, Core Concepts. Book number 4 and number 5. Book number 4 is Structure of Domination in Graphs. Number 5 is Topics in Domination, edited by the same two persons, Haynes, Hedetneimi, and Professor Michael Henning. And I am also author some chapters on this, one chapter of each of these books. But using graph theoretical approach to the Cockayne graph, we can associate a graph to a chessboard according to chess pieces. For example, for the original problem of Cockayne problem, you can associate a vertex to every square of a chessboard. For example, in the 2x2 chessboard here, you put one vertex in each square, and you make adjacent the vertices according to the movement of the queen that was vertically, horizontally, and geometrically. So this graph in the right side graph, this right side graph is the graph associated to the movements of queens in a 2x2 chessboard. Then the next graph in the following graph, this is a graph associated to the movements of queens in a 3x3 chessboard. So for the queen problem, the queen problem in the general case can be considered as a domination problem in the associated graph, and we call this graph as Q index n. Using this method of associating graphs to chessboard, Weekly and others answered the problem, the queen problem, for n up to 132. For example, for this amounts of m, the domination number is n over 2. It means that in a n by n chessboard, the minimum number of queens attacking all squares of the queen is n over 2. For this n, the answer is n over 2 plus 1, and for these n's, the answer is between n plus 1, n over 2 and n over 2 plus 1. For other n's, the problem is still remains open. There are a lot of applications for domination problem and the idea of domination in graphs. For example, for locating radar stations that ask that a number of strategic locations are to be kept under surveillance. The goal is to locate a radar for to cover all places on the territory. This is actually a dominating problem. For example, in the communication in networks, in biological networks, social networks, and many other branches of mathematics and science, it has many applications. Okay, now we present several upper bounds for the domination number of a graph. The most trivial, the first trivial upper, the bound in the domination is this bound. For any graph of order n, the domination number is between 1 and n. It is very trivial. We can easily check that the domination number is equal to 1 if and only if your graph has a universal vertex, and the domination number is equal to n if you have an edgeless graph. And here you can you have two examples. You see two examples of the domination number equal 1 or n. A special kind of domination is minimal dominating sets. a minimal dominating set. A minimal dominating set is a dominating set such that no proper subset of it is also a dominating set. You can see very easily that if S is a minimal dominating set, then the complement of S, that is G minus S, is also a minimum dominating set. In the general case, this is not true, but for minimal dominating sets, this is true. Using this trivial observation, Ore in 1962 proved this upper bound. The domination number of any graph with no isolated vertex is bounded above by n over 2. The proof is very easy using the above mentioned fact. If you have a minimal dominating set, namely S, then both S and S complement are dominating set. So one of them has cardinality at most n over 2, and so this bond will be proved. The main question is that how can we improve this bond and we give other better bonds for the domination number? Many efforts have been done to improve this end of n over 2 bonds of Ore. The first attempt have been taken. The first person in this topic here was Payan and others, who characterized graphs achieving equality for the Ore's upper bound. You know that Ore proved that the domination number is bounded above by n over 2. So the problem is here, which graphs satisfies the equality of this? Payan proved that the domination number is n over 2 if and only if either G is a cycle of order 4 or the coronagraph of a graph H, which the coronagraph of a graph H denoted by core H is a graph obtaining by H from H by attaching a vertex to every vertex of H. For example, here you see the coronagraph of K7. So you add a leaf to every vertex of the K7 to obtain the coronagraph of K7. Okay, the next example you see here the coronagraph of P8. But there is a property here that if gamma G is equal to n over 2, then n should be even because the domination number is an integer. But what happens for odd n? Here you see two families of graphs, family A containing 7 graphs, and you have family B here. Cockayne and others try to characterize graphs with domination number is equal to n over 2, this amount, and they studied and derived some properties of these graphs, and finally they constructed 3 families of graphs G1 until G6, and they finally characterized all graphs G with gamma G is this value. In attempting to trying to improve the Ore's n half bond, in 1989, for minimum degree at least 2, it is proved this upper bond. If the minimum degree is at least 2, then your domination number is at most 2n over 5, and you see here 2n over 5 is less than n half. So This is actually an improvement of Or's upper bound for minimum degree greater than or equal to 2. Reed in 1996 considered minimum degree at least 3 and proved that for these classes of graphs, the domination number is bounded above by 3n/8. And this is better than the previous upper bound. Cockayne et al. and others considered and studied the same problem for minimum degree at least 3, and they noticed that if a graph is class-free, then the domination number is bounded above by this n/3. You know that a class-free graph is a graph that does not contain a class as an induced subgraph, and you know a class is a star of order 3. Of order 4. This bound even improved previous upper bound. You know, n/3 is less than 3n/8. In 1990, Caro and his colleagues considered the minimum degree at least 7, and they proved this upper bound. So for minimum degree between 4 and 6, the problem remains open, and we don't know better upper bounds for the domination number for in the case minimum degree equal 4, 5, and 6. But for larger minimum degrees, there are other upper bounds, and we report them. You see here an upper bound proved independently by four papers that says that the domination number of a graph G is bounded above by n dot this amount, this value. As an observation, if we consider this part of this bound, the function fx equal 1 plus ln 1 plus x/1 plus x is decreasing. It can be easily checked by a calculus. It means that when x is increases, then this function will be decreases. So if your minimum degree delta is increased, then your domination number will be decreased. So for larger delta, for example, for any larger and larger minimum degree, this bound is better than all of previous given bounds in the domination number, for the domination number. Alon also proved that for sufficiently large n, there are graphs satisfying the previous upper bound asymptotically. 2 years ago, I improved the bound of Alon and others, and this part is the bound of Alon and others, and we here subtract this amount of their bound, and so this is better bound from their bound. This is also with another upper bound for the domination number has been obtained by the same technique as previous theorem. And this bound is better than Caro and we bound that we stated them. There are a lot of other bounds for the domination number involving other graph theory parameters, graph variance. For example, here you see a bound that says the domination number of any graph G is bounded above by n minus maximum degree and bounded below by n over 1 plus maximum degree. The graphs achieving the graph satisfying the equality of this bound are not known by now. But for the class of trees, Domk and others proved that a tree T satisfied the equality of the previous upper bound if and only T is a wounded spider. A wounded spider is a tree that obtained from a star by adding a leaf to any leaf of the star. This is healthy spider, and a wounded spider is a tree obtained from a healthy spider by removing some of the leaf, but not all leaves. So the problem of characterizing graph achieving equality for this upper bound is still open. The same also is for the lower bound. You see here also several other upper bounds. For example, Flat and Wolfman proposed this upper bound in terms of both minimum and maximum degree of the graph. And Payan also presented another upper bound, as you see here. You see here's a bound in 1997 from Sanchez, who proved that the domination number is bounded above by m plus 2/3 where m is the size of the graph. Size means the cardinality of each set. Other bounds in terms of size of the graph are obtained. For example, here you see another upper and lower bounds for this domination number involving the size of the graph by Berge and Vizing, and you see here. There are also other upper bound and lower bound for the domination number in terms of the size of the graph and involving other parameters of the graph. Here you also see two bounds involving the diameter and the girth of the graph. For any connected graph G, the domination number is bounded below by diameter of G plus 1/3, and you see also here an upper bound in terms of the girth of the graph. When X state some reports some developments taken in the Vizing conjecture. The Cartesian product of two graphs G and H, denoted by G box H, is the graph obtained from G and H, such that the vertex set is the Cartesian product of vertices of the vertex sets of the graph G and H, and two vertices U prime and V prime are adjacent in G box H if and only if one of the following holds. The first is U equal V and U prime is adjacent to V prime in H, or the converse. U prime is equal V prime and U is adjacent to V in G. And you see here an example of two graphs. This graph, the left side and right side, the product of this graph, the Cartesian product of these two graphs are depicted here. Vizing conjectured in 1962 that the domination number of the Cartesian product of two graphs is greater than or equal to the product of their domination number. This conjecture by now is still open, and a lot of the effort have been done to prove or disprove this conjecture, but all notice that this conjecture is true for several classes of graphs. So a graph G is defined to satisfy Vizing conjecture, or in some papers it refers as Vizing graph. A Vizing graph is a graph G that this inequality holds for any graph H. So if your graph G is a Vizing graph or satisfied Vizing conjecture, it means that for any graph H, the Vizing conjecture holds for this graph G. Among a lot of efforts to prove the Vizing conjecture, in 1979, it is proved that any graph with domination number, at most 2 satisfies Vizing conjecture. In 2004, the above result has been extended for gamma equal to 3. So at the moment, any graph with domination number at most 3 satisfies Vizing conjecture. In 1991, Hartnell and Raval proved that if a graph G satisfies Vizing conjecture and K is a spanning subgraph of G with equal domination number, then K also satisfies Vizing conjecture. There are many other results devoted in Vizing conjecture. For example, it is proved that any tree satisfies Vizing conjecture, and there are a lot of research trying to present lower bound similar Vizing conjectures, and they refer them Vizing-like bounds. For example, Elzahar and this person in 1991 proved that the domination number of G box H is greater than or equal from the minimum cardinality of orders of G and H. This is very trivial, and we can prove it very easily. Jacobson in 1983 proved the following lower bound for the domination number of Cartesian products of two graphs G and H. Jacobson and Nietzsche proved this lower bound for the domination number of Cartesian product of two graphs G and H, and this bound involved the domination number and two packing number of a graph. There are another lower bound involving the domination number of the graphs G and H and their packing number here, presented by Suen and others. Clark and Suen in 2000 proved that for any graph G, for any two graphs G and H, the domination number of G box H is bounded below by this value. And in the following, you see a bound proved by several persons in 2009, and they proved that the domination number of G box H is greater than or equal 1/2 alpha G dot gamma G plus 1, where alpha G stands for the independence number of the graph, that is the cardinality of a maximal independent set of a graph. The Vizing conjecture for other domination parameters under name Vizing line conjecture have been also studied by several other peoples. We next state report some algorithmic and complexity aspects of the domination number, and the first is a linear algorithm for trees. Cockayne and others proved and presented a linear time algorithm to compute the domination number of a tree. But for the complexity point of view, the decision problem associated to domination number is here. The instance of the decision problem is that a graph G and the positive integer K, and the question is that whether does G have a dominating set of cardinality K? Gary and Johnson proved that the domination problem, the decision problem associated the domination number is NP-complete in the general graph. They used it. They used the known complexity result of the 3-sat. We know that 3-sat is an NP-complete problem, and the 3-sat is a fundamental problem in the theoretical computer science. They proved a reduction, made a reduction from the 3-sat to the domination problem, and proved that the domination problem is NP-complete for the class of general graphs. Later, some other researchers improved the previous complexity results, and Chang et al. Proved that the domination problem is NP-complete for the class of bipartite graphs. And Booth and others proved that it is also NP-complete for chordal graphs. It is proved that the domination problem is in the class P. In the class P for the families of block graphs, interval graphs, permutation graphs, and several other classes of graphs. The term P here refers to the class of polynomial time, polynomial problems. It means that there is a polynomial time algorithm to compute them. And also, it is proved that the domination number is NP-complete for the class of chordal graph, weakly chordal graph, chordal bipartite graph, and a lot of other classes of graphs. There are models of domination in graphs. And here you see some fundamental parameters, fundamental variation of domination. The first one is the original domination number. A subset S is a dominating set if the closed neighborhood of S contains all vertices of the graph. We have discussed this in this meeting mostly about this variation. The minimum cardinality of this set was called the domination number, and it was denoted by gamma. You can also consider the maximum cardinality of it as the maximum domination number, and it is denoted by big gamma. There are a lot of bounds and results on the maximum domination number, and you can refer to references and to books to study them. If you have a dominating set such that S, you have a dominating set such as S and S is independent, then you have a model of domination, namely independent domination. The minimum cardinality of an independent domination is denoted by IG, and the maximum number is alpha. If you have a dominating set such that dominating set namely such as S, such that the open neighborhood of S equal to the vertex set of the graph, this dominating set is called the total dominating set. The minimum cardinality of a total dominating set is called the total domination number, and it is denoted by gamma T. The same, likewise, we can have maximum cardinality of a total dominating set as denoted by big gamma. If you have a dominating set and your set, the induced subset of the set S has a perfect matching, it is called the paired dominating set. The minimum cardinality and maximum cardinality are denoted by gamma PR and big gamma PR. If you have a dominating set and the induced subgraph of S is connected, you have a connected dominating set, and minimum and maximum cardinalities are denoted by gamma C and big gamma index C. There are conditions on the dominating set. For example, for another example, if you have a dominating set that the induced subgraph by S has no cycle, then it is called acyclic domination. If your the induced subgraph of your dominating set S is bipartite, this is called bipartite domination. If your set induces a clique, it is called clique domination. And also we have private domination. We have semi-paired domination, semi-total domination, weakly connected domination, convex domination, weakly convex, cycle domination, equivalent domination, K-domination, K-dependent domination. There are conditions on the complement of your dominating set. For example, if any vertex outside the dominating set S, for any vertex outside your dominating set S, there exists a vertices whose distance with V is at most K, it is called distance K domination. If this inequality change to equality, this will be called K step dominating set. You have also the term K domination, restraint domination, geodetic domination, locating domination, which is very important to identifying codes. Secondary domination, downhill domination. Each of them, in each of these topics, you will find tens or more, maybe hundreds of papers. Secondary domination, downhill domination, exponential domination, fair domination, outer connected, and other kinds of domination. You can also consider some conditions on the vertex set, and for total dominating set we have discussed already. Some other types are odd domination, even domination, identifying code number, total distance K domination, K tuple domination. There are also conditions on the vertex degree, and these conditions produces some new variation of domination. Degree condition on both S and S complement, degree condition per vertex, dominating functions. The concept of domination can be considered and can be viewed in terms of functions. You can, when you have a dominating set S, so you can assign number one to each vertex of S and 0 to each vertex outside S. So you can consider, you can view the domination as a function, as a functional point of view. Roman dominating function, stratified domination, domination chain, conditions relating to perfection, critically parameters. All of these are topics, and you can find these topics. Some of them are chapters in the books I already introduced you. Partitions and domatic numbers, rainbow domination, and other kind of domination. If you have any suggestion or question and consultation with me, you can contact with me by this email, and this is my WhatsApp number. Thank you very much for your attention. If you have any question, I am ready.
Okay, thank you, Prof. Nader, for your presentation. So, to all participants, if you have any question, you can unmute yourself or you can use the chat box. Any question from the participant?
Hi, welcome, Prof. So I'm Yao here. So I just want to check, right, do you aware that are there any researchers that actually working to improve the graph algorithms in determining the dominating numbers for some classes of graphs? Are there any researchers that are actively working on graph algorithms on this topic?
Yes. In the book I introduce you, there are some chapters in devoting on algorithmic aspects, and I can send you the book if you need. You can see a lot of researchers have been researched in the algorithmic aspects. I only presented and reported in this talk only NP completeness, but there are many other computational complexity results, and I have not included in my talk here, but they are in the books, and you can follow the book.
I see, because from what I can see in your talk, right, you actually introduce many different types of dominating numbers in there, and do you know, is there any polynomial time algorithms to determine any type of the dominating numbers that you have to introduce, or most of them are actually NP complete?
Most are NP complete. Actually, other than the class of trees, for other big classes of graphs, they are NP complete. But there are surely very polynomial time algorithms for classes of graph. For example, in block graphs, in trees, and in some for some parameters in the class of cactus graph, we have also algorithms.
I see. All right. Thank you.
Thank you. Okay.
Okay. Prof, we have one question here from the Tehran from School of Mathematical Sciences exam. The question is, since the Vizing conjecture appears to be wide open, has any researcher stands off the side that the conjecture might be false, or an attempt to find a counterexample? You get the question?
I think there is no counterexample, and it is hardly if somebody can obtain counterexamples. Many research, all research by no confirm the Vizing conjecture. No research by no disprove it. I think it is not. It is. I personally think it is not possible that you find a counterexample.
Okay, and then we have another question here. What type of domination? I mean, is there any new type of domination number that is introduced? Something different from the one you mentioned?
I mentioned the topic, several topics. For example, I stated that I have shown the topic Roman domination. It is introduced in 2004, but trying to improving results on the concept of domination in the area of Roman domination, there are very new types of Roman dominating function. For example, perfect Roman domination number, or total Roman domination number, or disjunctive total Roman domination number. Each of them has some recent developments, and you can find most of them in the books I addressed you.
So we have seen several different type of domination number. So which is the most studied domination number?
The main original variation is domination number, but the other variation, all other variation are important. It depends to the researchers. One researchers like total domination. One researchers is working on Roman domination, but all of them are variation of graphs, and I think most of them are interesting.
We have one more question here. Prof, the question is the problem of improving bounds, upper and lower. Is it continuing process and never stop?
Yes, yes, I'm continuing. Yes.
So the researchers keep improving the bound again and again.
Yes, yes, yes. It's for the bounds I presented in this talk are just some examples, some sample bounds. There are many research. For example, I presented an upper bound for Claffey graphs. They tried to improve previous bounds in the class of Claffey graphs. So, but you can also see that there are a lot of bounds in, for example, C4 free graphs, C5 free graphs, or for example, graphs that does not a graph that does not contain cycles, for example, C4 until C7. There are a lot of such bounds, and all of these bounds are bounds improving previous bounds with in some special classes of graphs. And it was not possible for me to include all of these bounds in this talk.
Okay, we have one more question from Dr. Teh. Regarding the chess problem, to your best knowledge, has any researchers attempt to study a variation where it involves a combination, say, knight and bishop at the same time?
Sorry, I have not got your point. Can you repeat it?
Has any researcher attempts to study a variation where it involves a combination, say, knight and bishop at the same time for the chess problem?
Yes. In the book I introduce you, there is a chapters, namely domination with other chess players, with other chess pieces, and there are many results in bishops. Many results for example, rooks, and you can see these research in the book.
What about the combination? Is there any research for the combination? Say, yeah.
No, I don't.
Two chess pieces. No,
I don't know. No, I don't know. But maybe it is. Interesting, maybe not, because the approach, as if you remember, the first chess piece problem was the problem of putting or placing some queens in the chessboard, and the first approach for this was number theory, but they had not enough progress, so they decided to consider and use the graph theory, and in the graph theoretical points of view, you should associate a graph to the movement of your chess piece. So if you have two chess pieces, you should think how you associate the graph. I think maybe it is not possible. I don't know, but maybe not possible.
Okay, one more question here. K-step domination, can you explain more the motivation? For example, K equals 2.
K equal to means that if you have a dominating set, what is a dominating set? A dominating set is a subset, say S, such that every vertex outside S is adjacent to one vertex of H. This is domination. So here you can consider a further condition. Your further condition is here. Any vertex outside S is adjacent to at least two vertices of S. This is called two domination. If every vertex outside S is adjacent to k vertices of S, this is called k domination. Okay?
And okay, one more question. What is your opinion about relation between domination number or its variation with other graph problem or parameter like graph indices, graph labeling, or Hamiltonian problem?
There are many relations. For example, the bonds. There are relations in terms of bonds, mainly in terms of bonds. For example, as you saw in this talk, I presented several bonds involving various graph parameters. For example, you know that the domination number is, for example, bounded above by a formula involving the order of the graph, the chromatic number of the graph, the size of the graph, the independence number, the diameter, and other graph parameters. This is up to the researchers that can drive some properties and according to them obtain some bound in term for the domination number in terms of other graph theory variation. But there are also some domination parameters. For example, there is a domination parameter, namely outer connected. If you search, you can see many papers in the area of outer connected domination. Under name outer connect is outer independent domination. So outer independent domination is a dominating set that has a further property that the outside of S is independent. It is proved that, you can also prove this, it is proved that the outer independent domination number of a graph is equal to the vertex covering number. So it is proved that these two graph variation are equivalent, are equal. So maybe it is possible that somebody else prove, for example, total domination number is equal to, for example, another graph variation. I don't know. This is depend to researcher and the results already obtained in this area. And since I have talked about total domination, in the next meeting I will show that the total domination number of a graph is also equal to another variation, namely transversal, and I will explain more in the next talk.
Okay, any other question?
Sorry, Prof, I have one more question. So when you first define the dominating set problem, it seems to me that this problem is very much similar to the vertex cover problems. So may I know, is there any relationships between these two problems? Because in your case, we basically focus on vertices, but in vertex cover problems, we actually have to make sure that every edge is covered by at least one vertex. So is there any relationship, relationship between these two problems?
Yes, I already told you. For example, outer connected domination, you have a dominating set that its complement does not have any edge. Okay, so any edge has at least one point in your set. So your dominating set is actually a vertex cover. You know what is a vertex cover? A vertex cover is a subset of vertices such that any edge covers any edge. Okay, so your domination, your outer independent dominating set is actually a vertex cover.
I see. You mentioned this in your talk just now.
No, I have not mentioned this because the topics were very huge and very large. I had not find a chance to explain about all of them. I only presented mostly titles. For example, in the last slides, you saw a lot of titles that each of these titles are chapters, are in each of them. For example, I only mentioned the term Roman domination, but I still do not have not defined for you. But if you see you search in the area of the Roman domination, you see, I think maybe 400 papers or 300 papers are published in the area of Roman domination. So there are many results.
Okay, thank you.
Thank you.
So, okay, any other question? Okay, we have one more question here. Prof, vertices in dominating set should not be adjacent, right? Dominating set, not necessarily, right, Prof? Vertices in dominating set should not be adjacent.
Sorry,
No.
I don't.
Vertices in dominating set should not be adjacent, right? No,
Yes.
Should not
for
be
the
adjacent.
dominating set, you should your vertices outside should be adjacent to some vertex of the S, the set. But what's the problem?
But the vertices in the dominating set can be adjacent, right?
No, not necessarily.
But can, right?
Yes, if the term the adjacent, you should precisely explain what is adjacent. If all of them are adjacent, then actually your dominating set induces a clique. So here you have clique domination, and I mentioned it. But if you mean by adjacency that each vertex is adjacent to another one, it means that you have no isolated vertex. If you have no isolated vertex, then you have a dominating set, namely total dominating set. If you mean by adjacency that there is a path from each vertex of the set to another vertex of the set, then you mean that your dominating set induces a connected graph. So this is a connected dominating set. So this, according to these conditions, there are types of dominations.
Okay, any other question?
Hello.
Yes.
I think Dr. Ruslan.
Ruslan here. Nader. Can you hear me?
Yes. Hello, Dr. Ruslan.
Yeah, well, it was very nice talk. Just one short question.
Yes.
What is the most difficult part, the most difficult problem in your study in domination problem? Or domination, or in the domination number, or its variation?
Actually, your question has not a trivial answer. It depends. For example, some researchers that, for example, such as Professor Michael Henning, one of the main central persons in the domination. He is focused on the area of total domination. So if you ask this question from Professor Henning, maybe he asks you, he say a problem, he tell you a problem on the total domination. But maybe somebody else say for domination, say maybe somebody say for another type of domination. It depends to researchers and the problems they still cannot prove. But generally speaking, in all of the kinds of domination, I think providing bonds, lower bonds on upper bonds, which is best possible, is the main problem and the main difficult problem in the domination. And the researchers actually you see a lot of bonds. These efforts are trying to answer that problem and to approach the best upper bound. So you should provide best upper bounds in the domination number, and I think generally speaking this should be an answer, but in specified for any specified parameter, maybe different problem exists.
Okay, any other question from the participant? No more question? Okay, so if no more question, then I think, okay, on behalf of School of Mathematical Sciences USM, I would like to thank Prof. Nader for your presentation. Thank you very much. And to those who are interested in to do research in domination, maybe you can contact Prof. Nader via his email. And so any info on the second talk will be posted on our Facebook page, School of Mathematical Sciences USM. And I think that's all for this seminar. So I think we can end this seminar. Thank you everyone for joining this presentation, and stay safe. Thank you.
Thank you.
Thank you very much. Thank you very much to all of you. Thank you. Goodbye.